Welcome to Still Science Lab. Tonight we explore a quiet question hidden beneath everything familiar. What if the universe is hiding something, not in the distant stars, not beyond the edge of the observable cosmos, but beneath matter itself? Not a secret in the dramatic sense, not a conspiracy of nature, but a deeper layer of reality that our current theories can sense, measure, and predict in fragments while still not fully explaining what it means. At night, Earth can feel simple. Cities glow along coastlines. Oceans move in darkness. Clouds drift over continents. Satellites pass silently overhead, carrying signals through the upper atmosphere. From the surface, the world appears stable, solid ground, familiar matter, air, water, light, gravity, motion. The universe seems distant, spread across the sky in stars and galaxies, as if its deepest mysteries are always far away. But some of the strangest questions in science do not begin with the farthest galaxy. They begin here, inside atoms, inside particles, inside fields that fill what we casually call empty space. Deep underground, detectors wait beneath layers of rock, shielded from the noise of the surface world. They sit in darkness, listening for rare disturbances. A faint flash, a tiny recoil, a trace of energy from something that may pass through ordinary matter, almost untouched. These instruments are built around patience. They are designed for the possibility that some of the universe's most important ingredients may not shine, may not reflect light, and may not announce themselves except through the smallest possible interaction. In other places, particle accelerators guide beams of matter through enormous rings and tunnels. Particles are pushed to extreme speeds, then collided under conditions controlled with extraordinary precision. For a fraction of a moment, energy becomes a doorway. New particles may appear and vanish almost instantly. Known particles scatter into complex patterns. Detectors record what remains. Tracks, decays, missing energy, and tiny deviations from expectation. Elsewhere, telescopes collect light from the edge of the observable universe. They study ancient radiation, distant galaxies, gravitational lensing, and the large-scale structure of the cosmos. They ask why galaxies rotate the way they do, why space expands the way it does, and why the universe contains so much invisible influence beyond the matter we can see. These searches may seem separate. One looks inward, into the quantum world. One looks outward, into the cosmic dark. But they may be connected by the same question. What is reality made of when the familiar picture is no longer enough? The quantum level is not simply small. It is not just a lower floor beneath atoms, where tiny objects behave like miniature versions of ordinary things. It is where reality stops behaving like the world our senses evolved to understand. It is where particles can act like waves, where empty space is filled with fields, where probability is not merely ignorance, and where information can belong to relationships rather than individual objects. At human scale, matter feels solid. A hand touches a table and meets resistance. A stone falls. A door opens or closes. A planet follows an orbit. The world seems made from clear objects with clear positions and predictable motion. This picture works well enough for life, engineering, and everyday survival. But quantum physics tells us that this familiar world is not the foundation. It is what the foundation becomes after countless interactions make it stable. Beneath the surface, matter is stranger. Electrons are not tiny planets circling atomic nuclei. Photons are not little glowing beads traveling through empty space. Particles, in modern physics, are better understood as excitations of quantum fields, localized events in something deeper and more spread out than ordinary objects. Even empty space is not simply nothing. It contains fields. It has structure. It allows fluctuations. It defines what kinds of particles can appear when energy is present. The vacuum is not an absence of reality, but a state of reality. This is already enough to unsettle the old picture. But the quantum world goes further. A quantum system may not always carry one definite answer before measurement. Instead, it can be described by a state containing possible outcomes and the probabilities of those outcomes. That does not mean anything can happen. It does not mean nature is chaotic. Quantum physics is one of the most precise scientific frameworks ever created. Its predictions have been tested with extraordinary accuracy. The mystery is not that quantum physics fails. The mystery is that it works while describing a reality that feels almost impossible to picture. A particle can be detected at one location, but the pattern of many detections may reveal wave-like behavior. A quantum state can describe possibilities before a measurement. Yet a detector records one result. Two particles at a time become entangled so that the full information about the system cannot be separated into independent parts. The relationship between them becomes part of the state. This does not allow faster-than-light communication. It does not break reality, but it does show that reality is deeper than separation, solidity, and certainty. At the quantum level, information can hide in correlations. Matter can arise from fields. Possibility can have structure. Measurement can turn an open range of outcomes into a recorded fact. These are not philosophical decorations, added after the science is done. They are part of the tested machinery of the physical world. And still, something seems missing. The standard model of particle physics describes known particles and three fundamental forces with stunning success. It explains ordinary matter better than any previous framework. It predicts results that experiments later confirmed. It revealed that the world beneath atoms is governed by deep patterns of fields, symmetries, and interactions. But the standard model does not explain everything. It does not tell us what dark matter is. It does not explain dark energy. It does not fully include gravity. It does not completely explain why neutrinos have the masses they do. It does not explain why the universe contains more matter than antimatter. These are not small details. They are signs that our map may still be incomplete. The universe is not broken, but the map may not reach all the way down. That is the central mystery. When scientists say the universe may be hiding something at the quantum level, they do not mean reality is unknowable or supernatural. They mean that the known laws, powerful as they are, may be one layer of a deeper structure. There may be particles we have not detected, forces we have not named, fields that interact only faintly with ordinary matter, hidden sectors that shaped the early universe and still influence the cosmos through gravity, dark matter, or subtle quantum effects. Some of these possibilities may be wrong. Many signals disappear with better data. Many anomalies turn out to be noise, background, or misunderstood known physics. Science protects itself through skepticism, repetition, and careful measurement. A mystery must survive doubt before it becomes discovery. But the fact that the questions remain matters. Dark matter continues to shape galaxies without revealing its identity. Black holes continue to raise deep questions about information and gravity. Quantum measurement continues to challenge simple ideas about what it means for reality to become definite. Entanglement continues to suggest that the universe may be built not only from objects, but from relationships. The hidden layer may not be far away. It may be underneath every familiar thing, inside the atoms of the body, inside the light from stars, inside the vacuum between galaxies, inside the first moments of the universe when tiny quantum fluctuations may have become the seeds of cosmic structure. The smallest rules may have shaped the largest patterns. That is why the question reaches beyond physics and becomes quietly existential. We live at a scale where reality looks stable. We experience a world of objects, memories, distances, and causes. But beneath that stability is a deeper order, one that does not always resemble the world it produces. The universe may be understandable not because it is simple, but because it has layers, and quantum physics may be the place where those layers first become visible. Not clearly, not completely, but enough to show that the familiar world is not the whole story. At night, when the sky seems still, the mystery is easy to place far away, in distant galaxies, black holes, or the first light of the universe. But the deeper mystery may also be present in every particle, field, every interaction, every quiet piece of matter resting in darkness. What if the universe is hiding something beneath matter itself? The answer is not yet known, but the search has already changed what we mean by reality. It has shown us that solidity can emerge from fields, that certainty can emerge from probability, that separateness can hide entanglement, that empty space can hold structure, that the visible universe may depend on invisible rules still waiting to be understood. The universe is not less real because it is strange. It is more profound because the surface is only the beginning. The quantum world feels impossible because the human mind was not built to understand it. Our senses evolved in a different layer of reality, a warmer layer, a larger layer, a world of stones, trees, bodies, rivers, tools, weather, and fire. A world where objects appear solid, where places seem clear, where causes seem to lead smoothly into effects. We learned to survive by trusting the scale we could touch. A branch is here, a predator is there, a cliff has an edge, a thrown object follows a path, a sound comes from a direction, a body moves through space one moment at a time. This is the classical world. It is the world that shaped intuition, and for everyday life, intuition works well enough. We expect objects to have locations. We expect them to keep their properties when we are not looking. We expect motion to be continuous. We expect the future to follow from the past. We expect measurement to reveal what was already true. If a cup sits on a table, it is on the table whether anyone checks. If a door is closed, it was closed before we opened our eyes. If a ball is thrown, it travels through the air along a path. That is the world our nervous systems were trained to model. But the quantum world is not built for human convenience. It exists beneath the scale where our senses operate. It governs particles, atoms, photons, fields, and interactions too small, too fast, and too delicate for direct perception. It is not strange because it is irrational. It is strange because it follows rules that were never needed for survival at human scale. Common sense is not a universal law, it is a local adaptation. At the quantum level, the idea of a solid object becomes less simple. A particle is not always best imagined as a tiny ball, moving through space like a miniature planet. An electron can behave in ways that resemble a wave. A photon can spread through an experiment as a probability structure, then arrive as a single detected event. Matter can produce interference patterns, even when individual detections appear one by one. This does not mean particles are pretending to be waves. It means the words particle and wave come from the classical world, and neither word fully captures what quantum systems are. A quantum object can produce localized events when measured, but before measurement, its behavior may be described by a state spread across possibilities. Those possibilities are not fantasies. They are not vague guesses. They follow precise mathematical rules. They can interfere with one another. They can reinforce some outcomes and cancel others. The result is a world that refuses to act like tiny versions of familiar objects. This is where intuition begins to fail. In everyday life, probability usually means incomplete knowledge. A coin is hidden under a hand, but it has already landed heads or tails. A card lies face down, but it is already one card and not another. We may not know the answer, but we assume this answer exists in a definite way before we look. Quantum probability is different. In quantum physics, probability appears to be built into the structure of prediction itself. A quantum state tells us what outcomes are possible and how likely they are. It does not always tell us exactly what will happen in one single event. It tells us the pattern reality will follow across many repeated events. That is a strange kind of certainty. Not certainty about one outcome, certainty about the shape of uncertainty. A single quantum event may be unpredictable, but repeated many times under the same conditions, the outcomes form a pattern that quantum theory predicts with extraordinary accuracy. This is why quantum physics is not chaos. It is not a license for anything to happen. The quantum world may be probabilistic, but it is not arbitrary. Its probabilities are disciplined. Its uncertainty has structure. That structure is one of the most successful discoveries in the history of science. It explains atoms. It explains light. It explains the behavior of electrons in materials. It explains lasers, semiconductors, atomic clocks, and much of modern technology. The quantum world feels impossible, but it is not vague. It is precise enough to build machines from. It is strange enough to challenge reality, but reliable enough to power civilization. This is the tension at the heart of quantum physics. It does not behave like our world, but our world depends on it. Measurement makes the tension deeper. In the classical world, measurement seems passive. We measure a table and assume the length was already there. We check a switch and assume it was already on or off. Measurement simply reveals the fact. In quantum physics, measurement is more subtle. A quantum system may be described by a range of possible outcomes before measurement. When measured, one outcome is recorded. The detector clicks. A value appears. The quantum state that once contained structured possibilities now leaves behind a definite fact. This does not mean human consciousness creates reality. That is not the careful scientific point. Measurement means physical interaction. A photon is absorbed. A particle strikes a detector. An atom changes state. A system becomes correlated with a measuring device, then with the environment. The result becomes stable enough to be recorded, copied, and shared. But even with that careful definition, the mystery remains. Before measurement, the quantum description contains possibilities. After measurement, the world contains one result. Does the measurement reveal something that already existed? Or does the interaction help create the outcome? Physicists still debate the deepest meaning. The calculations work. The experiments agree. But the interpretation remains one of the most profound, open questions in science. That is why quantum physics can feel unfinished, even though it is extraordinarily successful. It gives us results. It gives us predictions. It gives us technology. But it does not give us an easy picture. Entanglement pushes even harder against intuition. In our everyday view, objects separated by distance should have independent properties. One thing is here, another thing is there. Each carries its own information. If they influence each other, something must travel between them. But entangled quantum systems do not fit that simple division. When particles are entangled, the full information about the system may not belong to either particle alone. It belongs to the relationship between them. Measuring one particle can reveal correlations with the other that are stronger than anything classical physics allows. This does not allow faster-than-light messaging. No usable signal can be sent instantly across space. But it does show that separateness is not as simple as it seems. At the quantum level, information can belong to a connection, not just to an object. The whole can carry information that cannot be recovered by describing the parts separately. This is deeply unnatural to human intuition. But again, it is not vague. Entanglement has been tested in laboratories around the world. It is used in quantum information science. It is one of the most carefully studied features of quantum mechanics. The strangeness is real because the evidence is real. The quantum world feels impossible because it violates expectations we never realized we had. We expect objects to be solid. Quantum physics gives us fields and excitations. We expect properties to be definite. Quantum physics gives us states, probabilities, and measurement. We expect distance to separate things cleanly. Quantum physics gives us entanglement. We expect empty space to be empty. Quantum field theory tells us it contains fields, fluctuations, and possible excitations. The problem is not that the quantum world is irrational. The problem is that our instincts were trained by a simplified surface of reality. That surface is not false. The classical world is real. Tables exist. Planets orbit. Buildings stand. Machines work. Human life unfolds at a scale where quantum strangeness is usually hidden by countless interactions with the environment. The definite world emerges from quantum world, but it does not reveal every rule beneath it. That is why reality can feel ordinary while being built from something extraordinary. The ground is stable because quantum fields and forces create stable matter. The body is solid because atoms and electrons follow quantum rules. The sun shines because quantum processes allow nuclear reactions to happen. The technology around us works because quantum behavior can be controlled and engineered. The world we experience is classical, but its foundation is quantum. This is not a contradiction. It is a layering. The mistake is expecting the foundation to look like the surface. A wave in the ocean does not look like a water molecule. A living cell does not look like the atoms that compose it. A thought does not look like the chemistry that supports it. Large-scale reality can emerge from deeper rules that do not resemble the world they produce. Quantum physics is one of the clearest examples of that truth. The universe is not obligated to match the hot categories human beings developed for everyday survival. It does not have to be made of tiny solid objects just because solid objects are familiar to us. It does not have to be deterministic in the classical sense just because certainty feels comfortable. It does not have to keep information only inside separate objects just because separation sets at human scale. The universe follows its own rules, and those rules are stranger, more subtle, and more precise than intuition expected. That is why the quantum world does not behave like ours. Or more accurately, our world is only one expression of the quantum world, seen after its deeper strangeness has been softened by scale, interaction, and complexity. Beneath the familiar surface, reality behaves through fields, probabilities, correlations, and measurement. It is not anything can happen. It is something far more interesting. Only certain things that have the rules results deciding them are not the rules our senses were designed to understand. The quantum world feels impossible because we evolved to navigate the result, not the foundation. And science is the slow act of learning to hear the foundation speak. Matter feels certain. A hand rests on a table and the table pushes back. A stone has weight. A wall has resistance. A planet holds its shape beneath gravity. The physical world seems solid, made from things that occupy space, press against one another, and remain where they are until something moves them. This is the world our senses report with confidence. But at the quantum level, that confidence begins to dissolve. Not because matter is unreal. Matter is real. The table is real. The stone is real. The bodies is real. The stars are real. But the deeper question is what that reality is made from. And modern physics tells us that matter is not built from tiny solid balls in the simple way our imagination first suggests. Particles are not little pebbles moving through empty space. An electron is not a microscopic planet. A photon is not a tiny bead of light. A quark is not a hard grain trapped inside a proton. These images can be useful for a moment because the human mind wants pictures. But if we take them too literally, they become misleading. The quantum world is not a miniature version of the classical world. It is something deeper. In modern physics, particles are better understood as excitations of quantum fields. A field is not just a region of influence drawn on a diagram. It is a physical entity spread throughout space, capable of carrying energy, interacting with other fields, and producing what we call particles when it becomes excited in specific ways. Every known particle is associated with an underlying field. Electrons are excitations of the electron field. Photons are excitations of the electromagnetic field. Quarks are excitations of quark fields. The Higgs boson is associated with the Higgs field. The particles detected in laboratories are not separate little objects placed into an otherwise empty universe. They are local manifestations of fields that extend across space. This changes the story of matter completely. The universe is not empty space filled with particles. It is fields everywhere, with particles appearing as quantized disturbances within those fields. A particle is real, but it is not real as a tiny marble. It is real as an event, an excitation, a localized expression of a deeper structure. When a detector records a particle, it records the point where that field excitation interacts with the instrument. The event can be sharply localized, but the underlying description is not the same as a small solid object following a simple classical path. This is why particles can behave in ways that feel impossible. They can produce localized detections, yet also show wave-like behavior. They can interfere with themselves in experiments. They can be described through probabilities before measurement. They can belong to fields whose presence is not limited to a single point. The word particle survives because it is useful, but the old picture of a particle as a tiny hard thing is not enough. Even empty space is not truly empty. That may be one of the strangest ideas in all of physics. The vacuum is not absolute nothingness. It is not a blank stage where matter sometimes appears. In quantum field theory, empty space is the lowest energy state of the fields that fill the universe. Even when no particles are present, the fields remain. They have structure. They have possible excitations. They can fluctuate in subtle ways. Nothing at the quantum level is not quite nothing. The vacuum is quiet, but not absent. This matters because it means reality is not built from objects placed inside a dead void. The void itself has physical content. The fields are there before the particles appear. The particles are what the fields do under certain conditions. With enough energy, a field can become excited, and what we call a particle can be created. When particles annihilate or decay, the fields remain. The deeper layer is not the particle. The deeper layer is the field. This is not easy to feel, because the world around us appears so firm. A table does not feel like field behavior. A mountain does not feel like quantum structure. A human body does not feel like an arrangement of excitations and interactions. It feels solid, continuous, and immediate. But solidity is not fundamental in the way it seems. Solidity is an emergent experience. When your hand presses against a table, the atoms in your hand do not truly touch the atoms in the table in the way two pieces of clay might touch in imagination. At the microscopic level, the sensation of contact comes mainly from electromagnetic interactions between the electrons and atoms in both objects, along with quantum rules that determine how electrons can occupy states. The atoms resist being pushed into the same configurations. Electromagnetic forces respond. Quantum principles enforce structure. The result at human scale feels like touch. The table feels solid because the fields and particles that make up your hand interact with the fields and particles that make up the table. The sensation is real. The resistance is real, but it is not the result of tiny solid spheres bumping surfaces together. It is the large-scale outcome of invisible interactions. The body interprets those interactions as solidity. The mind accepts solidity as the obvious nature of matter. Physics reveals the machinery beneath it. Atoms themselves are mostly structured space, but that phrase can also mislead. It does not mean matter is fake or empty in a casual sense. It means the atom is not a tiny filled ball. It is a quantum system, a nucleus surrounded by electrons occupying states shaped by electromagnetic attraction and quantum rules. Those electrons do not orbit like little planets. They exist in probability patterns governed by the structure of the atom. The stability of matter comes from these patterns. Atoms have allowed energy levels. Electrons fill states according to quantum laws. Molecules form when atoms share or exchange electron structure. Chemistry emerges from the way quantum systems arrange themselves. The solid world is made from this hidden order: a crystal, a metal, a tree, a bone, a drop of water. Each is a stable arrangement built from quantum fields and interactions. Each feels classical because it is large, warm, and constantly interacting with its environment. The fragile strangeness of individual quantum states becomes blended into the reliable behavior of everyday objects. This is how the familiar world emerges. Not by abandoning quantum physics, by being made from it. The illusion is not that matter exists. The illusion is that matter is simple. What feels like a solid object is a vast coordination of fields, particles, forces, and quantum constraints. It is stable because the underlying laws are stable. Speed. It has shape because atoms form structures. It resists touch because electromagnetic interactions and quantum rules prevent matter from collapsing into itself. If those rules were different, the world would not feel solid. Atoms might not hold together. Chemistry might not exist. Stars might not burn in the same way. Bodies, planets, oceans, and life could not form as we know them. Solidity is not a basic assumption of the universe. It is an achievement of quantum law. This is where the ordinary world becomes quietly extraordinary. Every surface is a quantum result. Every material is field behavior stabilized into form. Every object is an emergent pattern. The ground beneath us is not less real because it is built from fields. It is more remarkable. It means reality can produce firmness from something that is not firm in the everyday sense. It can produce objects from states. It can produce touch from forces. It can produce the classical world from quantum rules that do not resemble the classical world at all. The deepest layer we know is not made of little solid pieces. It is made of fields whose excitations appear as particles. Fields whose interactions create forces. Fields whose states define what kinds of matter can exist. This picture also explains why particles of the same type are identical. Every electron in the universe behaves like every other electron because each is an excitation of the same underlying electron field. The electron in an atom on Earth and an electron in a distant galaxy are not merely similar. They are manifestations of the same universal field, obeying the same rules across cosmic distance. That universality is one of the quiet miracles of physics. The matter in your body is local, but the fields behind it are cosmic. The same quantum fields that form atoms in your hand also operate in stars, nebulae, and galaxies billions of light years away. The same electromagnetic field that carries light from a distant star also governs the chemistry inside living cells. The same quantum rules that stabilize matter here stabilize matter across the observable universe. We live inside a reality that is deeply consistent, but not simple. When physicists say the universe may be hiding something at the quantum level, this is part of what they mean. The visible world may be only the surface expression of fields and interactions we have learned to describe, and perhaps others we have not. The known fields may not be the full inventory. There may be hidden fields, hidden particles, hidden sectors of physics that interact only faintly with ordinary matter. If the matter we know is field behavior, then unknown matter may be field behavior too. Dark matter, for example, may be made of particles associated with fields beyond the standard model. These particles might not feel electromagnetism. They might not shine. They might pass through ordinary matter almost unnoticed. Yet they could still shape galaxies through gravity. They could be real without being visible in the ordinary way. The idea sounds strange only because our senses are built around familiar matter. But physics has already taught us that visibility is not the same as reality. Most of what matter is doing is invisible to direct ears. We do not see electromagnetic interactions between atoms. We do not feel quantum states as quantum states. We do not perceive fields filling space. We experience the stable result: solidity, color, heat, pressure, texture, form. The surface is classical. The foundation is quantum. And perhaps beneath the foundation we know, there is still more. This is why the illusion of solid matter is not a dismissal of the world. It is an invitation to see the world more deeply. Matter is not an illusion in the sense of being false. It is an appearance produced by hidden structure. It is the way quantum fields, forces, and rules become meaningful at the scale of life. A table is real, but it is not real as a simple block of substance. It is real as an arrangement of atoms, electrons, fields, interactions, and quantum constraints. It is a stable pattern in the deeper machinery of the universe. The same is true of us. The body is not separate from this mystery. Every atom in the body is part of the quantum world. Every nerve signal, every chemical bond, every breath depends on matter behaving according to rules far beneath conscious perception. We are not observers standing outside quantum reality. We are made from it. And that may be the most profound part. The universe has built beings out of fields and particles, who can wonder what fields and particles are. It has formed minds from matter that is not solid in the way matter appears. It has created awareness from quantum-built structures capable of asking why anything feels real at all. Matter is real, but it is not built from little solid objects in the way we imagine. It is built from quantum states and fields, from invisible interactions and stable patterns, from a foundation that does not look like the world it produces. The solid world is what the quantum world becomes when its hidden rules are repeated across trillions of particles, locked into atoms, shaped into molecules, and gathered into the familiar forms of ordinary life. The surface is firm, the foundation is strange, and somewhere inside that strangeness, the universe may still be hiding a deeper layer of matter, waiting to be found. Probability is one of the quiet places where quantum physics breaks away from the world we think we know. In ordinary life, probability usually means that something is hidden from us. A coin is tossed, and before we look, we say there is a chance it landed heads and a chance it landed tails. But the coin has already landed. The answer is already there. Our uncertainty belongs to us, not to the coin. A card is drawn from a deck and placed face down. We do not know what it is, but the card itself is already definite. A storm may or may not arrive tomorrow. Not because the atmosphere has no structure, but because the details are too complex for us to follow perfectly. This is classical uncertainty. It is uncertainty caused by incomplete knowledge. The world has an answer. We simply have not found it yet. Quantum probability is different. At the quantum level, probability does not appear merely as a weakness in human knowledge. It appears inside the structure of the theory itself. A quantum state tells us what outcomes are possible and how likely those outcomes are. But it does not always tell us what will happen in a single event. It gives a pattern. It gives a distribution. It gives the shape of what repeated measurements will reveal. But it does not always give certainty. That is one of the deepest breaks from classical thinking. A quantum system is not always like a covered coin. already heads or tails before anyone checks. It is not always like a hidden card, definite but unseen. In many experiments, the best description of the system before measurement is not one fixed answer waiting in darkness. It is a structured range of possibilities, governed by precise rules. This does not mean reality is vague. It does not mean the universe has no order. It does not mean anything can happen. Quantum physics is not chaos dressed in mathematics. It is one of the most exact scientific frameworks ever created. Its predictions have been tested again and again, often to astonishing precision. But the kind of prediction it gives is not always the prediction our classical instincts expect. Quantum physics does not always predict one outcome. It predicts the pattern reality will follow over many events. Imagine a single quantum particle entering an experiment. The theory may tell us the probabilities of different possible results. It may say where the particle is likely to be detected and where it is unlikely to appear. But when the measurement happens, one result is recorded, one detector clicks, one mark is left, one fact enters the world. That single outcome may not have been predictable with certainty, but if the experiment is repeated many times, under the same conditions, the results begin to form a pattern. What looked uncertain once becomes orderly in repetition. The individual event is unpredictable. The long-term structure is precise. This is not a weakness of quantum physics. It is its strange strength. In the classical world, we tend to imagine that perfect knowledge would remove probability. If we knew every detail of a coin toss, the force, the spin, the air resistance, the surface, the angle, the timing, perhaps we could predict the result. If we knew every molecule in the atmosphere and every motion influencing the weather, perhaps the forecast would become exact. Classical probability often feels like a temporary substitute for knowledge we do not yet have. Quantum probability does not behave so easily, even when a quantum system is prepared carefully, even when the same preparation is repeated, even when the theory knows the state as fully as it can. The outcome of a single measurement can remain probabilistic, not because the experimenter is careless, not because the equipment is crude, not because some obvious variable has been forgotten. The probability belongs to the quantum description itself. That is unsettling. It means complete quantum knowledge may still not mean classical certainty. The quantum state can be fully specified, and yet the result of a particular measurement may still only be predicted as a set of possibilities. The universe gives a rule, but not always an individual answer in advance. This has led to long debates about what quantum probability really means. Some interpretations treat it as fundamental randomness. Others suggest that all possible outcomes may exist in a broader structure. Some ask whether hidden variables exist in quantum mechanics, though experiments have strongly limited what such hidden explanations can look like. The debate remains open because the mathematics is clear, but the meaning is difficult. Still, the experimental fact remains. Nature follows quantum probabilities, and those probabilities are not casual guesses. They are structured with extraordinary discipline. A quantum state is not simply a list of chances. It contains amplitudes, phases, and relationships that can influence how possibilities combine. Unlike ordinary probabilities, quantum possibilities can interfere. Some reinforce one another, some cancel. This is why particles can create interference patterns. The possible paths of a quantum system are not merely alternatives sitting side by side. They can shape one another before a measurement occurs. This is one of the reasons the quantum world cannot be reduced to common sense. If a particle were just a tiny object, secretly following one path, many quantum experiments would look different. The patterns we observe require something deeper. They require a description in which possibility itself has structure. A single particle may arrive as a dot, but the pattern of many dots reveals us a wave-like order. One event looks almost random. Many events reveal the hidden rule. That is the strange beauty of quantum probability. It does not remove law from nature. It moves law into the pattern. It tells us that reality may not always be governed by certainty at the level of individual events, but it is still governed. It is not disorder. It is lawful uncertainty. This distinction matters because quantum probability often sounds more mysterious than it really is, and sometimes less mysterious than it should. It is not simply the universe rolling dice in a careless way. The dice, if we use that image at all, are weighted by the quantum state, constrained by physical law, and repeated with consistency across experiments. But it is also not ordinary ignorance. It is not merely that nature has a hidden classical answer and we are too limited to see it. Quantum probability sits between those simple pictures. It is precise, but not deterministic in the old sense. It is uncertain, but not lawless. It is statistical, but deeply physical. This is why it has become one of the most important features of modern science. The stability of atoms, the behavior of light, the structure of materials, the timing of radioactive decay, the operation of lasers, the design of semi-centers, and the emerging power of quantum computers all depend on quantum probability. It is not an abstract philosophical problem kept away from technology. It is woven into the working machinery of the modern world. Radioactive decay is one of the clearest examples. An unstable atom has a probability of decaying over a certain time. For one individual atom, quantum theory may not tell us exactly when the decay will happen, but for a large collection of atoms, the pattern becomes reliable. Half-life is not a prediction about one atom. It is a prediction about many. The individual moment is uncertain. The collective behavior is precise. This is how quantum physics often speaks. Not always in single destinies, but in statistical laws. The same idea appears in particle physics. A particle produced in a collision may decay through several possible channels. Quantum theory can tell scientists the probability of each decay pattern. One event may choose one path, another event may choose another. But after many events, the distribution can match theory with extraordinary accuracy. Reality refuses certainty in the single case, then reveals order in the many. This kind of order is difficult for human intuition because we are used to stories about individual causes. We want to know why this particle went here and not there, why this atom decayed now and not later, why this measurement gave one result and not another. Quantum physics often answers differently. It says, here is the state, here are the possible outcomes, here are their probabilities, and here is the pattern that will emerge if the question is asked again and again. That answer can feel incomplete, but perhaps it only feels incomplete because we are asking for a classical story from a non-classical world. The quantum world does not always provide the kind of explanation our senses prefer. It provides the explanation nature seems to use. And that explanation works. This is where probability becomes almost philosophical. If the universe at its foundation does not always contain definite answers before measurement, then reality is not merely a finished script unfolding line by line. It is also a system of possibilities becoming facts through interaction. The future is not arbitrary, but neither is it always written in the old mechanical sense. A measurement does not create chaos. It selects an outcome from a structure of possibilities defined by the quantum state. The result becomes definite, a record forms. The world gains another fact, and still the deeper pattern remains probabilistic. This does not make the universe less real. It makes reality more subtle than certainty alone. The solid world we experience emerges from countless quantum events, interactions, and records. At large scales, the probabilistic nature of individual events becomes averaged, stabilized, and hidden inside classical behavior. We see objects, not amplitudes. We see surfaces, not probability distributions. We remember outcomes, not the full field of possibilities that preceded them. But beneath the classical surface, the quantum structure continues. Every atom carries it. Every photon obeys it. Every particle interaction reveals it. Every detector click is one fact drawn from a deeper law of possibilities. There is a quiet humility in this. Human beings evolved to navigate a world where certainty appears natural. We learn to predict falling objects, flowing water, animal movement, and the passing of days, but the universe did not build its foundation for our intuition. It built something stranger, a reality where individual events may resist exact prediction, while the patterns across many events reveal extraordinary order. Quantum probability is not the absence of knowledge. It is a different kind of knowledge. It teaches us that knowing the universe may not always mean knowing exactly what will happen next. Sometimes it means knowing the range of what can happen, the rules that govern those possibilities, and the pattern they will form when reality is measured many times. That is a profound shift. Classical certainty says the world has already chosen, and we are catching up. Quantum probability suggests that, at least in some deep sense, the world carries structured possibilities until interaction makes one of them actual. The universe is not broken by this. It is not irrational. It is not less scientific. It is more mysterious and more precise than the older map allowed. Quantum physics does not always predict one outcome. It predicts the pattern reality will follow over many events. And inside that pattern, beneath the uncertainty of single moments, we find one of the strangest forms of order ever discovered, a reality that refuses certainty, but never abandons law. Entanglement is one of the places where quantum physics becomes quietest and most disturbing, not because it is loud, not because it breaks the universe open in some visible way, but because it challenges one of the deepest habits of human thought, the belief that things are separate first and connected second. In ordinary life, separation feels obvious. A stone on the ground has its own properties. A lamp across the room has its own state. A star in the sky exists far away, distant from the body looking up at it. Objects seem to carry their own information. They have locations, shapes, motions, and histories. If two things influence each other, something must pass between them. A signal, a force, a collision, a wave of light, a transfer of energy. That is the classical picture. Objects exist. Space separates them. Connections happen through contact or signals. Entanglement tells us that, at the quantum level, this picture is incomplete. When two particles become entangled, the full information about the system cannot always be separated into two independent parts. It is not enough to say one particle has its own complete state, and the other particle has its own complete state. The relationship between them becomes part of the quantum state itself. The connection is not just a detail. The connection carries information. This is one of the strangest and most important discoveries in quantum physics. It means that a system can contain information that does not belong entirely to any one object inside it. The whole can be described in a way that the individual parts cannot fully explain on their own. At first, this sounds almost philosophical, but it is not only philosophy, it is experimental physics. Scientists can create entangled particles in laboratories. They can send them apart. They can measure them separately, and when the results are compared, the particles show correlations stronger than anything classical physics permits. The outcomes are not merely like two hidden cards placed in envelopes, where one card already says one thing and the other already says another. Entangled particles do not behave as if they simply carried ordinary secret instructions from the beginning. Nature does something more subtle. It creates a shared quantum state. This shared state can survive separation. The particles can move apart through space, and yet the mathematical description of the pair remains unified. Each particle taken alone may appear uncertain, but together their outcomes follow a deeper pattern. That pattern is the evidence. The information is hidden in the relationship. This idea unsettled some of the greatest minds in physics because it seems to challenge how distance should work. If two particles are far apart, how can measuring one be connected to what is measured about the other? Shouldn't distant objects have their own independent realities? Shouldn't information be stored locally, inside each particle, rather than in a relationship stretched across space? These questions are not naive. They are exactly the questions that make entanglement so important. But the answer must be handled carefully. Entanglement does not allow faster-than-light messaging. It does not let a person send a controlled signal instantly across the universe. It does not create a cosmic telephone. If two observers measure entangled particles far apart, each observer sees a result that appears locally random. Neither observer can choose the outcome in a way that sends a message to the other. Only later, when they compare their results through ordinary communication, do the correlations become clear. That comparison cannot happen faster than light. So, relativity is not violated. No usable information travels instantly from one side to the other, and yet the correlations remain. This is the careful mystery of entanglement. It does not give us science fiction communication. It gives us something stranger, a form of quantum relationship that cannot be fully explained by classical separateness. The particles do not behave like independent objects with complete private properties. They behave like parts of a single quantum system. This is why entanglement matters so deeply. It suggests that the universe is not always built from self-contained pieces. At the quantum level, reality may be partly defined by relationships. The properties of a system may not belong only to the objects we identify, but also to the structure connecting them. In classical thinking, information usually belongs somewhere. It is written on a page, stored in a device, encoded in a signal, attached to a particle, contained in an object. If we want to know the whole system, we imagine that we can gather the information from each part and assemble the complete picture. Quantum mechanics breaks that assumption. Primitive, in an entangled system, knowing everything about each part separately may still not give you everything about the whole. Some of the information belongs to the way the parts are correlated. It is not here or there in the ordinary sense. It is in the shared state. This is a profound shift. It means information can be relational. A particle can be less fully described alone than it is as part of a pair. The whole can be more fundamental than the separated pieces. The relationship can become a physical feature, not just a human description. This does not mean everything is mystically connected to everything else. Entanglement is specific. It must be created or preserved through physical processes. It is often fragile. Interactions with the environment can spread and degrade the useful form of entanglement. Large everyday objects do not usually show obvious entanglement effects because they are constantly interacting with air, light, heat, and countless surrounding particles. The ordinary world looks separate because quantum information becomes widely dispersed. The environment is always measuring in a physical sense. Light reflects from objects. Air molecules collide with them. Heat transfers through them. Every interaction carries away traces of information. The delicate quantum relationships that can be controlled in laboratories become entangled with too many degrees of freedom to track. The world becomes classical-looking, stable, and definite. But beneath that stability Entanglement remains a natural part of quantum theory. When particles interact, they can become entangled. When systems evolve, information can become distributed across relationships. When measurement happens, systems become correlated with detectors and environments. In this sense, entanglement is not a rare trick. It is part of the hidden machinery by which the classical world emerges from quantum rules. The familiar world may be built from entanglement we no longer see. That is one reason entanglement has become central to modern physics. It is not only a strange experiment, it is a resource in quantum information science. Quantum computers use entanglement and related quantum effects to process information in ways classical machines cannot easily reproduce. Quantum communication uses entanglement to create forms of security rooted in the laws of physics. Quantum teleportation, despite its dramatic name, uses entanglement to transfer quantum states with the help of ordinary communication, not to move objects or messages faster than light. Again, the real science is stranger than the fantasy, but more disciplined. Entanglement does not ignore the rules. It reveals deeper rules. Its importance may reach even further into the structure of space-time itself. Some modern research suggests that entanglement and quantum information may be connected to geometry, gravity, and the way space-time emerges at the deepest level. This is not settled science. It is an active frontier. But black holes, quantum information, and the search for quantum gravity have made physicists take the idea seriously. Perhaps space is not only a stage where entangled systems exist. Perhaps some aspects of space are related to patterns of entanglement. That possibility is difficult to imagine, and it should be approached with caution. It does not mean distance is fake. It does not mean the world is an illusion, but it does suggest that the geometry we experience may not be the final layer of reality. The closeness or separation of things in space may be connected at some deeper level to how quantum information is organized. If so, entanglement may not simply be a strange feature inside the universe. It may be one of the clues to why the universe has structure at all. This is where the mystery becomes larger than particles. Entanglement teaches that relationship can be physical. It teaches that information can be shared in a way no classical story can fully explain. It teaches that the whole can contain something not reducible to the parts. These lessons echo far beyond one experiment or one pair of particles. They challenge the way we think about reality. Human intuition is object-centered. We think in terms of things: a body, a planet, a particle, a star, a machine. But quantum physics asks us to think also in terms of states, systems, and correlations. It asks us to treat relationships not as secondary connections between already complete things, but as part of what defines those things. This does not erase individuality. It complicates it. A particle can still be detected in one place. An object can still have a stable form. A person can still exist as a distinct physical system. But at the quantum level, distinctness is not always the whole story. Systems can share information. Their histories can become linked. Their states can become inseparable in a mathematical and physical sense. The universe, beneath its ordinary appearance, may be less like a collection of isolated objects and more like a web of structured relationships. That idea should not be exaggerated, but it should not be softened too much either. Entanglement is not merely weird, it is telling us something. It tells us that the classical idea of separateness is not fundamental enough. It tells us that information can be distributed in ways our senses were never designed to perceive. It tells us that the boundary between things may be less absolute at the deepest levels of physics. And perhaps that is why entanglement feels so haunting. It is not violent. It is not cosmic in scale by appearance. It does not make the sky flash or matter collapse. It happens silently, in the mathematics of states, in the correlations between measurements, in the hidden order beneath events. But its implication is vast. Reality may not be built only from objects. It may also be built from connections. At the quantum level, information can belong to the connection, not just the object. A pair of particles can carry a shared state. A system can contain information in relationships that cannot be assigned to its parts separately. The distance between things can remain real, while still not fully describing how deeply they are connected. The universe is not less real because of this. It is more intricate, more layered, more difficult to reduce to the simple map our senses gave us. Entanglement does not let us send messages faster than light. It does not make physics magical. It does something quieter and more important. It reveals that beneath the visible world of separate things, nature can preserve a form of togetherness that classical physics never allowed. And somewhere inside that hidden togetherness, the universe may be keeping part of its deepest information. The Standard Model is one of the most precise maps humanity has ever drawn. Not a map of continents, oceans, or stars, but a map of the hidden structure beneath ordinary matter. It describes the particles that make up atoms, the forces that allow those particles to interact, and the fields that give the physical world its shape. At the smallest scales we can test. It is not the whole universe. But for the matter we know most directly, it is astonishingly powerful. Every object around us depends on the rules it describes. The air in the lungs, the water in speakers, the carbon in living cells, the silicon inside computers, the light from lamps, screens, and stars, the atomic structures that give matter form, chemistry, color, texture, and stability. All rest on the behavior of particles and fields described by this framework. The Standard Model is our best tested theory of known particles and three of the fundamental forces. It includes the matter particles, quarks and leptons. Quarks combine to form protons and neutrons, the particles inside atomic nuclei. Electrons, a type of lepton, surround those nuclei and make atoms possible. Other leptons include neutrinos, ghost-like particles that pass through matter with extraordinary ease, produced in nuclear reactions, radioactive decay, and violent cosmic events. These particles are not random debris. They come in families. They carry properties. They obey patterns. They have masses, charges, spins, and interaction behaviors. They are part of a deep order that physicists have measured with extraordinary care. The Standard Model also includes force carriers. Matter does not simply sit in the universe. It interacts. It binds, repels, transforms, emits light, absorbs energy, and forms structures. The electromagnetic force governs light, electricity, magnetism, atoms, and chemistry. The strong force binds quarks together and holds atomic nuclei together. The weak force allows certain particles to change identity and plays a critical role in radioactive decay and the processes that let stars shine. These forces are not just effects added on top of particles. They are part of the grammar of matter. They decide which particles can interact, which structures can form, which transformations are possible, and how the microscopic world gives rise to the world we experience. Then there is the Higgs field. The Higgs field fills space, and many particles gain mass through their interaction with it. The discovery of the Higgs boson, the particle associated with this field, was not just the discovery of one more object. It confirmed a crucial part of the Standard Model's architecture. It showed that something invisible and field-like, something present throughout space, was tied to one of the most basic properties of matter. This is the strength of the Standard Model. It takes invisible fields and turns them into testable predictions. It takes fleeting particles that exist for less than a fraction of a second and reconstructs them from their traces. It takes the chaos of high-energy collisions and reveals order underneath. Again and again, experiments have tested the Standard Model. Particle accelerators have collided matter at enormous energies. Detectors have recorded the debris. Physicists have compared what nature produces with what the theory predicts. The agreement has often been astonishing. This is why the Standard Model cannot be dismissed casually. It is not a vague sketch. It is not a theory built on hope. It is one of the most successful scientific frameworks ever created, and yet it has borders. The first border is gravity. The Standard Model does not include gravity in the same way it includes the electromagnetic, strong and weak forces. Gravity is described by general relativity, another enormously successful theory where mass and energy curve space-time. General relativity explains planetary orbits, gravitational lensing, black holes, and the expansion of the universe. But it is not fully united with quantum mechanics. The Standard Model speaks the language of quantum fields. Gravity speaks the language of space-time geometry. Both languages work, but they do not yet merge into one complete description. That is not a small omission. Gravity shapes the largest structures in the cosmos. It governs galaxies, stars, black holes, and the universe's expansion. If the Standard Model is a map of microscopic matter, gravity is the map of space-time itself. A complete picture of reality must eventually explain how these maps connect. Then there is dark matter. Across the universe, galaxies rotate as if they contain far more mass than what we can see. Galaxy clusters bend light as if surrounded by invisible matter. The cosmic web, the great structure of galaxies and voids, seems to require gravitational influence from something that does not shine. Dark matter appears to exist, but the Standard Model does not tell us what it is. There is no confirmed dark matter particle inside the known catalogue. If dark matter is made of particles, those particles may belong to physics beyond the Standard Model. They may interact very weakly with ordinary matter. They may be part of a hidden sector, real but almost invisible, felt mainly through gravity. This is one of the strongest clues that the known map is incomplete. The visible matter explained by the Standard Model may be only a small fraction of what the universe contains. Dark energy is another missing piece. The expansion of the universe is accelerating. Something appears to be driving space apart on cosmic scales. We call it dark energy, but that name is more a placeholder than an explanation. The Standard Model does not provide a satisfying answer for what dark energy is or why it has the value we observe. This mystery reaches into the nature of empty space itself. In quantum field theory, the vacuum is not nothing. It has fields, it has structure, it may have energy, but connecting that vacuum structure to the observed behavior of the universe remains one of the deepest unresolved problems in physics. The emptiest places in the universe may be telling us that our deepest theories still do not fully agree. Neutrinos add a quieter but important clue. They are part of the Standard Model, but their behavior has revealed that the simplest version of the theory was not complete. Neutrinos have mass, and they can change identity as they travel. These facts point toward additional structure beyond the original framework. Their masses are extremely small, but their implications are large. A tiny particle can reveal a deep missing mechanism. That is often how physics works. Then there is the matter-antimatter imbalance. The early universe should have produced matter and antimatter in nearly equal amounts. When matter and antimatter meet, they can annihilate into radiation. If the balance had been perfect, the universe might have ended up with almost no ordinary matter left to form stars, planets, oceans, or living beings. But matter survived. Galaxies exist. Earth exists. We exist. Something tipped the balance. The Standard Model contains some differences between matter and antimatter, but not enough to fully explain the universe we observe. There must be a deeper reason why matter outlasted antimatter, and that reason may involve particles or interactions beyond what we currently know. This is one of the most profound, unanswered questions in science. Why is there something material instead of almost nothing? The Standard Model gives us a magnificent account of the matter that survived, but it does not fully explain why that matter survived at all. These gaps do not mean the Standard Model is wrong in the simple sense. That would be too easy, and it would be misleading. The Standard Model works. It explains an enormous range of phenomena. Its predictions have been confirmed again and again. Any deeper theory must explain why the Standard Model succeeds so well. It cannot simply erase it. It must contain it, extend it, and reveal its limits. This is how great theories are usually replaced, not by being discarded like broken tools, but by being placed inside larger structures. Newton's laws still describe the motion of ordinary objects with great accuracy, even though relativity revealed a deeper picture of space, time, and gravity. Classical physics still works across much of everyday life, even though quantum mechanics revealed the strange foundation beneath atoms. In the same way, the Standard Model may remain true within its domain while still being only one layer of a deeper reality. That is the central idea. The Standard Model is powerful, but it may not be complete. It may be the visible floor of a much larger building. Below it, there may be hidden fields, hidden particles, hidden forces, hidden symmetries, structures that shaped the early universe, influenced dark matter, gave neutrinos their masses, or helped matter survive the birth of the cosmos. The known theory gives us the particles that build ordinary matter. But ordinary matter may not be the whole story. It gives us three forces with stunning precision, but nature may contain interactions that barely touch the visible world. It gives us the Higgs field and the structure of particle masses, but it does not fully explain why the masses have the values they do. It explains the atoms that form bodies, planets, and stars, but not the invisible matter holding galaxies together. This is why physicists keep searching. Not because the Standard Model failed, because it succeeded so deeply that its unanswered questions became impossible to ignore. A weak theory leaves confusion everywhere. A strong theory shows us exactly where the mystery remains, and the Standard Model is strong enough to reveal its own edges. At those edges, scientists look for faint signals, a particle that does not fit, a decay that happens too often, missing energy in a collision, a dark matter interaction in an underground detector, a tiny difference between prediction and measurement, a trace that suggests the known map has a hidden continuation. Most such hints will disappear. Some will become better measurements of known physics, but one of them may survive. And if it does, it could open a deeper layer beneath matter. That is the quiet suspense of modern physics. The map is brilliant, but not finished. The known particles form a beautiful structure, but the universe keeps whispering that something remains outside it. Dark matter, dark energy, gravity, neutrino masses, and the matter-antimatter imbalance are not empty gaps. They are shaped like questions. The Standard Model explains ordinary reality with extraordinary accuracy. But realities may not end with ordinary matter. Somewhere beyond the particles we know, beyond the forces already named, beyond the limits of the current map, the universe may still be hiding the next layer of its structure, not a contradiction of what we know. A deeper reason why what we know works at all. Dark matter is one of the quietest mysteries in the universe. It does not announce itself with light. It does not glow in telescopes. It does not form bright clouds, shining stars, or visible structures that can be photographed directly. It has no color, no surface, no ordinary shadow. If it is made of particles, those particles may be passing through Earth right now through stone, water, metal, air, and the human body. leaving almost no trace at all. And yet, on cosmic scales, dark matter is difficult to ignore. Galaxies rotate as if they are surrounded by more mass than their stars and gas can explain. In the outer regions of many galaxies, stars move too quickly to be held by the visible matter alone. If only the matter we can see were present, those stars should behave differently. The galaxy should not have the same gravitational grip. Something unseen appears to be helping hold the system together. Clusters of galaxies tell the same story in another way. They contain galaxies, hot gas, and enormous gravitational fields. When astronomers measure how these clusters move, how they hold together, and how they bend light from more distant objects, the visible matter is not enough. There appears to be additional mass spread through and around the cluster, shaping the path of light and the motion of galaxies. The cosmic web adds another clue. Across the largest scales, galaxies are not scattered randomly. They form filaments, walls, knots, and vast empty-looking voids. This structure grew over billions of years under the influence of gravity. But the growth we observe makes far more sense if invisible matter was present early, forming a gravitational scaffold. Ordinary matter made of atoms could then fall into that scaffold, cool, and form stars and galaxies. Dark matter is not a small correction. It may be part of the reason galaxies exist in the form we see today. The name itself is honest, but incomplete. Dark matter is dark because it does not interact with light in the ordinary way. It does not emit light like stars. It does not absorb light like dust. It does not reflect light like planets or moons. We know it mostly by gravity, by the way it pulls, bends, gathers, and shapes the visible universe. But gravity tells us only that something is there. It does not tell us what the something is. That is where the investigation begins. One possibility is that dark matter is made of particles. Not the familiar particles that form atoms, but particles beyond the standard model. They may have mass but no electric charge. They may not feel the electromagnetic force, which would explain why they do not shine. They may interact very weakly with ordinary matter, so weakly that almost all of them pass through planets and detectors without touching anything. A particle like that would be real, but almost invisible to us. Another possibility is even more layered. Dark matter may belong to a hidden sector of physics. A hidden sector is not a fantasy realm, it is a scientific idea. A set of particles and perhaps forces that exist beyond the known standard model, but interact only faintly with the particles that make up ordinary matter. This hidden sector could have its own structure, its own interactions, even its own history in the early universe. If that is true, dark matter may not be one simple ingredient. It may be part of an unseen world of particles and fields. Ordinary matter would be only the bright surface of a deeper physical reality. This idea is difficult to picture because human senses are built around electromagnetic interaction. We see because photons enter our eyes. We touch because atoms repel and bind through electromagnetic forces. Our instruments often begin with light, charge, heat, or motion. If something does not interact with light and barely interacts with atoms, it can be everywhere and still remain hidden. Visibility is not the same as existence. The universe may contain particles and forces that are real, but almost invisible to us. To search for them, scientists have to think like forensic investigators. They are not looking for dark matter in the way one looks for a stone on the ground. They are looking for traces, disturbances, imbalances, rare events, tiny deviations from what known physics predicts. Some experiments wait deep underground. The underground setting matters. At Earth's surface, detectors are constantly bombarded by cosmic rays and natural radiation. These ordinary backgrounds can produce signals that imitate something new, so scientists place detectors beneath mountains, inside mines, or under thick layers of shielding. Rock absorbs much of the unwanted noise. The deeper the detector, the quieter the environment becomes. Inside these underground experiments, materials are cooled, purified, and monitored with extraordinary care. The goal is to detect a dark matter particle if it happens to strike an atomic nucleus or disturb the detector in some tiny way. Such an event might produce a faint flash of light, a small electric signal, a vibration, or a recoil, so subtle that it would be meaningless without years of preparation. Most of the time, nothing happens, or rather, almost nothing that cannot be explained by known backgrounds. That silence is part of the search. A detector may wait for months or years, listening for a single event that stands apart from everything ordinary. But the event must be treated with suspicion. Was it natural radioactivity? A cosmic ray that slipped through? Noise in the electronics? A material impurity? A statistical accident? The search for hidden particles is not only a search for signals, it is a search for signals that survive every ordinary explanation. Particle accelerators take a different approach. Instead of waiting for dark matter from space to interact, they try to create hidden particles through high-energy collisions. When known particles collide with enough energy, that energy can produce new particles if nature allows it. Some of those particles may decay into visible products. Others may escape the detector without interacting. If an invisible particle is produced, scientists may not see it directly. They may see missing energy. In a collision, energy and momentum must balance. If the visible particles fly away in a pattern that does not account for the full event, something unseen may have carried energy away. Neutrinos already do this in known physics, so missing energy alone is not enough. But a pattern of missing energy, appearing in the right way and too often to be explained by known particles, could point toward hidden matter. Absence becomes evidence, not empty absence, but structured absence. A missing piece in an event that should have balanced. Scientists also search through rare decays. Known particles decay according to specific rules and probabilities. Some decays are common, others are extremely rare. If a decay happens more often than expected, or if it produces a final pattern that does not fit the standard model, it may suggest that a hidden particle or hidden force is influencing the process. The new particle may not appear directly, it may only change the odds. That is one of the subtleties of modern physics. A hidden particle can reveal itself by slightly altering the behavior of known particles. A rare decay rate, a tiny shift in a magnetic property, a small mismatch in a precision measurement. Any of these could become a clue. The hidden world may press lightly against the visible one, leaving only faint fingerprints in the data. Precision measurements are therefore another form of dark matter search. They do not always involve enormous collisions or underground chambers. Sometimes they involve measuring a known particle or atomic system with extraordinary accuracy, then comparing the result to theories. If the measured value disagrees with the prediction, and if every known source of error has been examined, the difference may point toward new physics. Maybe a hidden particle is contributing indirectly. Maybe a new field is influencing the system. Maybe the standard model is missing a small correction from a deeper layer, or maybe the discrepancy will vanish as theory and experiment improve. That uncertainty is part of the process. A quiet investigation must be patient. It must allow the possibility that the signal is real, while also assuming it may not be. Many promising hints fade. Some become better measurements of known physics. Some reveal flaws in detectors or calculations. Science does not become weaker when a signal disappears. It becomes more trustworthy. Dark matter demands that kind of discipline. The evidence for its gravitational effects is strong, but its particle nature remains unknown. The universe behaves as if unseen mass is present, But whether that mass is made of one particle, many particles, hidden fields, primordial objects, or something that forces us to modify gravity on large scales is still debated. The particle explanation is powerful, but it must be proven. This is why the search continues on multiple fronts. Underground detectors wait for rare impacts. Accelerators look for missing energy and new particles. Telescopes map the distribution of invisible mass through gravitational lensing. Cosmic surveys study how galaxies cluster and evolve. Precision experiments look for small deviations in known systems. Each method is incomplete alone. Together, they form a network of investigation, a global attempt to identify something that may make up much of the matter in the universe, while almost never touching the matter we are made of. There is something humbling about that. The visible world feels complete because it is all around us. Stars shine, galaxies glow, planets reflect light, dust clouds absorb and scatter radiation, bodies touch, breathe, and move through air. But all of this may be only the luminous fraction of a darker structure. The universe we see may be embedded in matter we do not see, shaped by particles that pass through our instruments like ghosts. And still, they are not supernatural. They are not outside physics. If dark matter particles exist, they obey laws. They have properties. They belong to fields. They may have formed in the early universe, gathered under gravity, and helped build the cosmic web. They are hidden not because they are unreal, but because their interactions with us are faint. The hidden does not have to be distant. It can be present and silent. This is the deepest tension in the dark matter search. The answer may be everywhere, yet nearly impossible to touch. The galaxy may be filled with a dark halo. Earth may be moving through a stream of invisible particles. Every second, countless dark matter particles may pass through the room, through oceans, through mountains, through living tissue, leaving no mark that ordinary senses can detect. To notice them, science has to build a new kind of sense. Not eyes, not ears, but detectors cooled in darkness, buried under stone, calibrated against the faintest backgrounds, and watched with the patience of decades. A new dark matter signal would not only solve a missing mass problem, it could open a hidden sector of reality. It could reveal particles beyond the standard model. It could show that the universe contains forces or fields that ordinary matter barely feels. It could connect the smallest events inside detectors to the largest structures in the cosmos. That is why this investigation feels so quiet and so vast at the same time. A tiny flash underground could explain the motion of galaxies. A missing energy event in a collider could point to matter that fills the Milky Way. A rare decay could reveal a hidden interaction that shaped the early universe. The smallest clue may belong to the largest mystery. For now, dark matter remains unseen. Its gravitational presence is written across the sky, but its identity is still missing from the map. It is one of the clearest signs that the universe may be hiding something at the quantum level. Particles, fields, or forces that are real but almost invisible to us. The search is not loud. It does not move quickly. It unfolds through silence, precision, and doubt. But somewhere in that silence, a detector may one day record a signal that does not fade, a disturbance that survives every ordinary explanation, a small mark left by the hidden matter around us. And if that happens, the invisible universe will have touched the visible one. A black hole is where the universe forces its deepest theories into the same room. Gravity becomes extreme. Quantum physics becomes unavoidable. Information, that quiet structure behind every physical state, becomes impossible to ignore. In most cases, these ideas can be studied separately. Quantum mechanics explains atom particles, fields, and microscopic events. General relativity explains gravity, space-time, orbits, galaxies, and black holes. Information theory helps describe what can be known, stored, hidden, transformed, or lost. But near a black hole, the boundaries between these subjects begin to blur. A black hole is not simply a dark object. It is a region of space-time where gravity has become so intense that, beyond a certain boundary, nothing can escape back to the outside universe. Not light, not matter, not ordinary signals. That boundary is called the event horizon, and it marks one of the most mysterious surfaces in all of physics. From far away, a black hole can seem simple. It has mass. It can spin. It may carry electric charge. But almost everything else about what formed it appears hidden. A star could collapse into it. Gas could fall in. Dust, radiation, planets, magnetic fields, and particles could cross the horizon. From the outside, the black hole settles into a state described by only a few basic properties. That simplicity is beautiful and deeply troubling, because everything that falls into a black hole carries information. A book carries information in the arrangement of ink on pages. A stone carries information in its atomic structure. A star carries information in its layers, composition, motion, temperature, and magnetic fields. A particle carries information in its quantum state. Even ordinary matter is not just mass and energy. It is arranged mass and energy. It has structure. It has history. So when something falls into a black hole, the question becomes unavoidable. What happens to that information? Is it destroyed? Is it hidden forever behind the event horizon? Is it scrambled beyond recognition? Or is it somehow returned to the universe in another form? This question is known as the black hole information problem, and it is not a small technical detail. It cuts directly into the foundations of physics. In quantum mechanics, information is not supposed to simply disappear from the universe. A physical system may become complicated. Its information may spread into correlations too subtle to recover. It may become effectively lost for any practical observer, but at the deepest level, quantum theory suggests that information should be preserved. The future should remain connected to the past. A black hole seems to threaten that connection. If matter falls in and the outside world loses access to all its detailed information, maybe the information is simply trapped. That possibility is strange, but not yet fatal. The information might still exist behind the horizon, inaccessible but not destroyed. But black holes may not last forever. Quantum effects near the horizon suggest that black holes can slowly emit radiation. Over immense spans of time, they can lose energy. They can shrink. In principle, they may eventually evaporate. Then the problem becomes sharper. If the black hole disappears, what happens to everything it swallowed? If only featureless radiation remains, carrying no detailed record of what fell in, then information seems to have been destroyed. But if quantum mechanics is right, that should not happen. The information must be preserved somehow. It may be encoded in subtle correlations in the radiation. It may be stored on or near the horizon. It may be scrambled into a form that no ordinary observer could ever reconstruct. But it cannot simply vanish. At least, not without changing something fundamental in physics. This is why black holes are not only objects in space. They are tests of reality's accounting system. They ask whether the universe keeps track of its own history. They ask whether information is as fundamental as matter and energy. They ask whether space itself has hidden microscopic structure. To understand why, we have to think about entropy. Entropy is often described as disorder, but that word can be too vague. A better way to think about entropy is as a measure of how many hidden microscopic states could produce the same large-scale appearance. A cup of warm gas may look simple from the outside. It has a temperature, pressure, and volume. But inside, its molecules can be arranged and moving in countless different ways. The more possible microscopic arrangements there are, the higher the entropy. Entropy is connected to hidden information, not necessarily information destroyed, but information we do not track in detail. A system with high entropy can look simple at the surface, while hiding enormous microscopic complexity underneath. This idea sits at the heart of thermodynamics, statistical physics, and the flow of time. But black holes make entropy stranger. A black hole has entropy, and its entropy appears to be connected not to the volume inside it, but to the area of its event horizon. That is a profound clue. In ordinary life, if we want to store more information, we usually think in terms of volume. A bigger box can hold more objects. A larger hard drive can contain more data. More space seems to mean more capacity. But black holes suggest something different. The maximum information associated with a region may be related to its boundary. The surface matters. The horizon matters. The edge between what can escape and what cannot may encode something deep about what lies within. This idea has reshaped theoretical physics. It suggests that information, gravity, and geometry may not be separate subjects. The structure of spacetime itself may be tied to the way information is stored and distributed. A black hole is not merely a place where matter disappears. It may be a place where the universe reveals that spacetime has an informational texture. That is why black holes sit at the quantum edge of gravity. General relativity describes them as regions where spacetime curves so intensely that horizons form. Quantum physics describes fields and particles that still exist near those horizons. Information theory asks what can be preserved, hidden, or recovered. All three meet at the same boundary, and none of them can be ignored. If we use only gravity, we miss the quantum radiation. If we use only quantum theory, we struggle with curved spacetime and horizons. If we ignore information, we cannot understand why black holes create such a deep paradox. The black hole becomes a kind of natural laboratory, not one we can enter, but one that forces the laws of nature into their most extreme form. Near the event horizon, time and space behave in ways that defy ordinary intuition. To a distant observer, infalling matter appears to slow and fade. To the falling object, crossing the horizon may not feel locally dramatic if the black hole is large enough. But after crossing, escape becomes impossible. The horizon is not a physical wall, yet it changes the causal structure of the universe. Information can go in, but can it come out? This question becomes even more haunting when we consider Hawking radiation. The radiation is not like a normal signal broadcast from the interior. It arises from quantum effects associated with the horizon. At first glance, it seems almost thermal, meaning it carries mainly information about the black hole's basic properties, not the detailed identity of what fell in. If the radiation is completely thermal, information is lost. If information is preserved, the radiation must carry subtle structure. Somewhere in the escaping particles, there must be correlations that remember the past. But how? That question has driven decades of debate. And while many physicists now believe information is preserved, the full story remains unfinished. Some ideas suggest that the information is encoded in the radiation over time. Some connect black hole horizons with holographic principles, where information about a volume can be described on a boundary. Some point towards space-time emerging from quantum entanglement or deeper informational relationships. These are frontier ideas. They are not simple answers, but they all share one lesson. Black holes seem to be telling us that information is not optional. It may be woven into gravity itself. This is where the mystery expands beyond black holes. If information is connected to horizons, entropy, and spacetime geometry, then perhaps spacetime is not as smooth and fundamental as it appears. Maybe what we experience as geometry has microscopic degrees of freedom. Maybe gravity emerges from deeper patterns of quantum information. Maybe the shape of space is related to how information is distributed and entangled. That does not mean space is fake. It means space may be layered. Just as matter appears solid at human scale, but becomes quantum fields at deeper scales, space-time may appear smooth at cosmic scale, while hiding quantum structure underneath. Black holes may be the places where that hidden structure becomes visible, not directly, but through paradox. A paradox is not always a contradiction in nature. Sometimes it is a contradiction in our understanding. Black holes may be showing us exactly where our theories are incomplete. Quantum mechanics says information should be preserved. General relativity says horizons hide regions from the outside. Thermodynamics says black holes have entropy. Quantum field theory says black holes radiate. All of these ideas are powerful. All of them are supported in their own ways. But together, they produce tension. That tension is a guide. It points toward deeper physics. The black hole information problem has become one of the clearest clues that the universe may be hiding something at the quantum level. Not simply a new particle, though new particles may exist. Not simply a new force, though hidden forces may be possible. But a deeper connection between information and the structure of reality itself. The question is no longer only what matter is made of, it is what reality remembers. If an object falls into a black hole, does the universe keep a record of it? If the record is scrambled, where is it stored? If it returns through radiation, how is it encoded? If space-time has microscopic structure, what are its fundamental degrees of freedom? If information is preserved, what does that reveal about the laws beneath gravity? These questions are difficult because they reach beyond ordinary experience. Human beings live far from black hole horizons. We move through weak gravity, familiar matter, and stable time. We do not feel space-time as something quantum. We do not experience information as part of geometry. But black holes operate where our everyday categories break down. They are dark not only because light cannot escape, they are dark because they hide the limits of our current map. And yet, they may also be where the next map begins. There is a quiet irony in that. The places that seem to erase information may be teaching us that information cannot be erased. The objects that appear simplest from the outside may contain the deepest complexity. The horizons that hide matter may reveal that reality itself is built from relationships between quantum theory, entropy, and space-time. A black hole is an ending for anything that crosses its horizon, but for physics, it is a beginning. It begins a question that cannot be avoided. What is preserved? What is hidden? What is returned? What does the universe do with information when gravity becomes absolute? The answer is not fully known. But the search for it has already changed how physicists think about reality. It has made information central. It has made black holes part of quantum theory. It has suggested that gravity may not be understood without entropy, and that space-time may not be understood without quantum information. Black holes may be where the hidden quantum rules of the universe become impossible to ignore. They are not only cosmic monsters. They are not only collapsed stars. They are the places where matter, gravity, time, entropy, and information meet at the edge of what science can currently explain. And somewheres near that edge, behind the silence of the horizon, the universe may be holding one of its deepest answers. Maybe the universe is not hiding only a new particle. Maybe it is hiding a deeper rulebook. That possibility sits at the edge of modern physics, where the questions become difficult to separate from philosophy, but remain grounded in mathematics, experiments, and the pressure of unresolved facts. For more than a century, physics has pushed downward into matter. Molecules gave way to atoms. Atoms gave way to nuclei and electrons. Nuclei gave way to protons, neutrons, quarks, and gluons. Particles gave way to quantum fields. And now at the frontier, even fields may not be the final layer. This does not mean fields are wrong. Quantum fields are among the most powerful ideas science has ever developed. They explain particles, interactions, forces, radiation, and much of the structure of matter. They allow physicists to predict experimental results with astonishing accuracy. If we ask, what are electrons, photons, and quarks are in our best current framework, the answer is not tiny solid objects. They are excitations of fields that fill space. But physics has learned to be careful with the word final. Every time a layer of reality begins to look complete, the universe reveals a deeper question. Particles seemed fundamental until fields became the better language. Space and time seemed fixed until relativity showed that they bend, stretch, and depend on motion and gravity. The vacuum seemed empty until quantum theory made it a structured state of fields. Now the question is whether particles and fields themselves emerge from something deeper. This is not settled science. It is an active area of research, but it is serious enough to shape some of the most important work in theoretical physics. The reasons is simple. Our current theories are powerful, but they do not yet form one complete picture. Quantum mechanics describes matter and energy at small scales. General relativity describes gravity and space-time at large scales. Both work brilliantly. Both have been tested. Both are essential. But when we try to combine them at the deepest level, the picture becomes incomplete. Black holes expose the problem. The early universe exposes the problem. The question of what space-time is made of, exposes the problem. Somewhere beneath quantum fields and curved space-time, there may be a deeper structure that gives rise to both. One of the most intriguing clues is quantum information. Information may sound abstract, almost too human to belong to the foundation of physics. But in modern science, information is tied to physical systems. It is stored, transformed, hidden, scrambled, and preserved through physical processes. A quantum state contains information about possible outcomes. Entanglement stores information in relationships between systems. Black holes force physicists to ask whether information can ever be destroyed. Again and again, information refuses to stay secondary. It begins to look structural, not a substance, not a material, not a ghostly layer floating above matter, but a way of describing what physical systems can be, how they can relate, and what can happen when they interact. This is where the frontier becomes strange. Some modern approaches suggest that space-time itself may be connected to quantum information. Perhaps geometry is not the starting point. Perhaps distance, connection, and even the smooth fabric of space emerge from patterns of entanglement beneath the surface. Entanglement already tells us something profound. In quantum mechanics, the full state of a system cannot always be reduced to the states of its individual parts. The relationship between particles can carry information that belongs to the whole, not to either particle alone. The connection becomes part of the physical description. Now, imagine extending that idea further. Maybe the shape of space is related to how quantum systems are connected. Maybe what we call distance is not fundamental, but emerges from deeper patterns of relationship. Maybe gravity is not simply a force acting through space, but a large-scale expression of how information and geometry are organized. These are not final answers. They are possibilities being explored, but they point toward a powerful reversal. We usually imagine reality as objects placed inside space. First, there is space, then things occupy it. Particles move through it. Forces act across it. Events happen within it. Space feels like the stage, and matter feels like the actors. But what if the stage itself is not fundamental? What if space emerges from deeper quantum rules? What if matter, force, and geometry are not separate ingredients, but different expressions of a more basic structure? This is difficult to picture. because the human mind is trained by the world after emergence. We experience space as obvious. We experience distance as basic. We experience objects as separate. We do not experience the quantum relationships that may underlie these things. We live in the large-scale result, not the microscopic foundation. But science has already shown that many familiar properties are emergent. Temperature is real, but it is not a separate substance. It emerges from the motion and energy distribution of many particles. Sound is real, but it emerges from collective vibrations through a medium. Solidity is real, but it emerges from quantum fields, electromagnetic interactions, and atomic structure. Life is real, but it emerges from chemistry organized into self-maintaining systems. Emergence does not mean illusion. It means a higher-level reality built from deeper rules. So, if space-time is emergent, that would not make space unreal. It would mean space has a deeper origin. It would mean the geometry of the universe is not the final foundation, but the large-scale form of something more subtle. This possibility has become especially important because black holes suggest that information and geometry are linked. A black hole has entropy, and that entropy is connected to the area of its horizon. That fact hints that the information associated with a region of space may be tied to its boundary, not simply its volume. It is as if the universe is telling us that space, information, and gravity are part of one deeper language. Physicists do not yet know the complete translation, but the clues are difficult to ignore. Another clue comes from the search for quantum gravity. Gravity, in general relativity, is not like the other forces. It is the curvature of space-time itself. But quantum mechanics tells us that the deepest behavior of matter is probabilistic, field-based, and information-rich. To unite them, we may need more than a small adjustment. We may need a new way of thinking about what space-time is. Maybe space-time is woven from quantum entanglement. Maybe gravity arises from changes in information. Maybe geometry is the large-scale shadow of a deeper quantum network. Maybe particles and fields are not the final actors, but patterns inside a deeper structure of relationships. Each idea is incomplete. Each must be tested where possible. Each carries uncertainty. But the direction is clear. The frontier of physics is no longer only asking what particles exist. It is asking why there is a stage for particles at all. This changes the meaning of the hidden quantum level. At first, it seems natural to think the universe may be hiding a new particle. Dark matter may be a hidden particle. A new force may require a new messenger. A rare detector signal may point to physics beyond the standard model. These are powerful possibilities, but a deeper possibility remains. The universe may be hiding not only new ingredients, but new rules. Not just another particle in the catalogue, not just another force added to the list, but a more basic framework from which particles, fields, space, time, and gravity emerge together. That is a much quieter mystery than a dramatic discovery headline. It does not offer an easy image. It does not announce one object that explains everything. It asks for patience. It asks for new mathematics, new experiments, and new ways of thinking. And yet, if true, it would change the foundation of reality more deeply than any single particle. Because the question would shift from, what is the universe made of? To, what rules allow the universe to appear as matter, space, and time? Maybe reality is not built only from objects in space. Maybe space itself is part of what gets built. Maybe matter is not the final substance, but a stable expression of fields. Maybe fields are not final either, but arise from deeper informational relationships. Maybe forces are not only interactions between things, but patterns that emerge from hidden symmetries and structures beneath the visible world. This is not mysticism. It is the sober edge of physics, the part where the known theories work beautifully, but still leave behind questions too deep to ignore. Why does gravity not fit naturally into the standard model? What happens to information in black holes? Why does space-time seem smooth if quantum physics governs the deepest scales? How did the early universe turn quantum fluctuations into cosmic structure? Why does reality have the particular fields, particles, and forces that it does? These questions may not have separate answers. They may be different faces of one deeper problem. The universe may be built from a rulebook that has not yet been fully read. And perhaps that is what the quantum level has been hinting at all along. Particles are not little solid objects. Matter is not as solid as it feels. Probability is not merely ignorance. Entanglement places information in relationships. Black holes connect information with gravity. Empty space has structure. Each revelation removes a layer of classical certainty. Each one shows that the familiar world is not the foundation, but the surface. A surface can be real, but it can still hide depth. The deeper rulebook, if it exists, may not look like anything human intuition expects. It may not be made of objects, or waves, or geometry in the ordinary sense. It may be a structure of quantum information, correlations, symmetries, and constraints. It may describe what can be known, what can happen, and how space-time itself becomes meaningful. For now, this remains frontier science. There is no final answer. No completed theory has yet replaced the known framework, but the search matters because it points towards the next layer of understanding. It suggests that the universe is not hiding because it is unknowable. It is hiding because reality is deeper than the tools we have so far built to describe it. The map is not false. It is unfinished, and somewhere beneath particles, fields, space-time, and gravity, the universe may still be holding the rules that make all of them possible. The universe is still keeping secrets, not because it is trying to hide from us, not because reality is designed to be unknowable, but because the maps we have built, powerful as they are, may still describe only part of a deeper structure. Science does not reveal the universe all at once. It moves layer by layer, from the obvious to the hidden, from the visible to the inferred, from the familiar surface to the quiet machinery beneath it. For a long time, the world seemed made of solid things. Matter had weight, objects had shape, space looked empty, time seemed to pass evenly. Distance separated one thing from another. A measurement revealed what was already there. The universe, at human scale, appeared stable and direct, as if reality had arranged itself in the same categories the human mind naturally uses. But quantum physics changed that. It did not make the world unreal. It made the world deeper. It showed that certainty is more subtle than it appears. In ordinary life, uncertainty often means we simply do not know enough. A hidden card already has a value. A coin under a hand has already landed. A distant object already has a location. But at the quantum level, uncertainty is not always just ignorance. A quantum state can describe a structured range of possible outcomes, and the theory may predict not one certain event, but the pattern reality will follow across many events. This is not chaos, it is disciplined possibility. A single event may resist prediction, while the larger pattern appears with astonishing precision. The quantum world does not abandon law. It reveals a different form of law, one that governs probability itself. Quantum physics also showed that separateness is more subtle than it appears. In the everyday world, objects seem independent. One thing is here, another is there. Distance divides them. But entanglement tells us that information can belong not only to objects, but to relationships. Two particles can share a quantum state in a way that cannot be reduced to the properties of each particle alone. This does not allow faster-than-light messages. It does not break reality. It reveals that connection can be more fundamental than classical intuition expected. At the deepest levels, the universe may not be built only from isolated pieces. It may also be built from correlations, shared states, and hidden relationships that do not fit neatly into the ordinary idea of distance. Quantum physics showed that solidity is more subtle than it appears. Matter feels firm. A hand rests on a table and meets resistance. A stone has weight. A wall has strength. But the solidity we feel is not the solidity of tiny hard balls stacked together. It is the result of quantum fields, electromagnetic interactions, atomic structure, and rules that determine how matter can occupy states. Particles are not little pebbles moving through a void. They are excitations of fields. Atoms are not miniature solar systems. They are quantum structures. The table is real, but its reality is not simple. Its firmness is an emergent fact, a large-scale result of invisible laws repeated across countless particles and fields. The solid world is what quantum structure becomes when it is stabilized into matter. Even empty space is more subtle than it appears. The vacuum is not absolute nothingness. It is not a dead stage waiting for particles to enter. In modern physics, empty space contains fields. It has structure. It has possible excitations. It can participate in the behavior of particles, forces, and perhaps use even the expansion of the universe itself. Nothing is not as empty as it seems. This is one of the quiet revolutions of science. The familiar world has become less obvious, but more meaningful. The universe is not less real because it is strange. It is more profound because every simple appearance points toward hidden structure. And still, the map remains unfinished. The Standard Model describes quantum particles and three fundamental forces with extraordinary success. It explains ordinary matter better than any theory before it. It gives us electrons, quarks, photons, gluons, neutrinos, the Higgs field, and the patterns that make atoms and chemistry possible. It is one of the great achievements of human thought, but it does not explain everything. Dark matter still shapes galaxies without revealing its identity. Dark energy still drives the accelerated expansion of the universe without giving us a clear physical explanation. Gravity still stands apart from the quantum framework that describes the other forces. Neutrinos still hint at deeper mechanisms. The existence of matter itself, rather than a universe almost erased by matter and antimatter, still asks for a deeper answer. These gaps are not failures, they are invitations. A mystery in science is not a wall. It is a boundary between what once be understood and what can still be discovered. The unknown does not weaken the known. It gives the known a horizon. The universe is not hiding something because it is beyond reason. It is hiding something because reality may have more layers than our current theories can reach. The hidden quantum level may contain new particles, hidden fields, unknown forces, or deeper rules connecting information, matter, gravity, and space-time. Or the answers may be stranger than any of those words. Black holes remind us how deep the question can go. They are places where gravity, quantum physics, and information meet in extreme tension. Matter falls in carrying structure, history, and quantum information. The outside universe sees only a few broad properties. If black holes radiate and eventually fade, what happens to everything they swallowed? Is the information destroyed, hidden, scrambled, or returned in a form too subtle to recognize? This is not only a question about black holes. It is a question about what reality remembers. It suggests that information may not be secondary. It may be part of the deep architecture of the universe. It may be tied to entropy, horizons, geometry, and the structure of space-time itself. The dark edge of a black hole may be one of the places where the universe quietly tells us that our categories are incomplete. Maybe space-time is not the final stage. Maybe gravity is not fully understood until it is connected to quantum information. Maybe particles and fields are not the last layer. Maybe reality is built from deeper relationships that only appear to us as matter, distance, force, and time. These ideas remain uncertain. They belong to the frontier, not to settled knowledge. That uncertainty matters. It protects the science from becoming speculation without discipline. A careful mind must distinguish what is known from what is possible, what has been tested from what is still being explored. But uncertainty is not emptiness. It is where science continues. Every great map of reality has had an edge. Beyond the edge, there was not nothing. There was more world. The edge of classical mechanics led to relativity and quantum theory. The edge of early atomic models led to fields and particles. The edge of the standard model may lead to hidden sectors, dark matter, quantum gravity, or a deeper understanding of information. The history of science is not a story of certainty replacing mystery forever. It is a story of better mysteries, more precise mysteries, mysteries shaped by evidence, measurement, and mathematics, mysteries that become sharp enough for the next generation of instruments to test. That is what makes the hidden quantum level so compelling. It is not vague darkness. It is not mystical emptiness. It is a set of clues scattered across physics, the behavior of particles, the structure of fields, the existence of dark matter, the silence of underground detectors, the missing energy in collisions, the entropy of black holes, the persistence of quantum probability, and the strange togetherness of entanglement. Each clue is incomplete alone. Together, they suggest that the familiar world is not the whole story. The human mind lives in the middle scale. We are too large to see quantum states directly and too small to feel the structure of the cosmos as a whole. We stand between particles and galaxies, between atoms and black holes, between the tiny and the vast, and from this narrow scale we try to understand all scales. That effort is fragile, but it is also remarkable. The universe has produced observers made of quantum-built matter. Who can ask what quantum matter is? It has produced minds inside space-time that can ask whether space-time is fundamental. It has produced life under ordinary stars, capable of wondering whether dark matter, hidden fields, or quantum information shaped the galaxies long before life existed. We are small, but we are not blind. Our senses are limited, but our instruments extend them. Our intuition is classical, but our mathematics can reach beyond intuition. Our theories are incomplete, but they can still touch real structure. Science is not the possession of final answers. It is the discipline of approaching reality carefully enough that even the unknown becomes meaningful. The universe is still keeping secrets, but not all secrets are meant to remain hidden forever. Some wait for better detectors. Some wait for clearer mathematics. Some wait for longer observations. Some wait for a pattern to grow stronger with more data. Some wait for a question to be asked in the right way. And some may be hidden so deeply that they change what you mean by matter, space, time, and information when they finally come into view. That is not a reason for fear. It is a reason for humility. The universe is not broken because we do not yet understand it completely. Reality is not unstable because our maps are unfinished. The world remains real. The stars still burn, atoms still hold together, gravity still gathers galaxies, light still travels across the dark. Life still exists on a small planet, asking questions beneath a sky filled with ancient signals. Mystery does not erase the world, it deepens it. The known universe is already extraordinary, but the unknown beneath it may be even more important. Beneath matter and light, beneath the apparent certainty of the everyday world, beneath the silence of empty space, there may still be hidden rules, shaping everything we see and everything we cannot yet see. The universe is not less real because it is strange. It is more profound because Beneath matter and light, it may still be keeping its deepest rules hidden in the quantum dark. Good night, and see you in the next video.